Today I'm going to talk about shared memory parallel programming. So we are going to talk about OpenMP, which is used for shared memory machines. During this presentation, I will talk. To follow this webinar, you need, I assume that you have already some basic knowledge of C, C++, or and Fortran, and you know also how to use the GNU compiler and Intel compiler, which means you need a compiler to compile your program in order to run it. To have access to the examples, you need to have Compute Canada account and WestGrid account. If you have this account, you will be able to connect to Grex. So in the next slide, I will show you how to connect. So once you connect, you will be able to copy the example to your home directory and run the example as during this webinar. So to connect to Grex, you need an SSH client. So if you are using Linux machine or Mac, you have already a terminal. So you just use the terminal and use SSH. If you are under Windows, you can use PuTTY, for example. In order to edit the example to the files, you need an editor. So the simple editor and the most flexible editor I suggest is VI. Some people use other editors with interface. It's very slow, so it's better to learn VI. Now, once you open your SSH, your terminal, you need to connect to Grex. So to connect to Grex, simple. So just SSH your username, the username you have on WestGrid at grex.westgrid.ca. Once you type this, it will ask you for a password. When you type nodes, you will end up on Tatanka or Bison. There are two login nodes. So I will do the same thing at the same time as you. So I have to switch to the terminal. So for example, I've already connected, so I don't have to type again. Now, once you are connected, you need to copy the examples from. There is a path on this slide, and please don't copy path from the slides because it gives you some hidden characters and it will not work. It's better to type the whole path. So cp minus r because we are going to copy a folder, so recursively. So this is the path / global scratch workshop OpenMP WestGrid October 2017. And don't forget the dot at the end of the command because you are going to copy this folder to your home directory. So I will copy now the folder to my home directory, cp minus r global scratch workshop OpenMP WestGrid 2000 October 2017 dot. Now we'll go so change directory, cd this directory OpenMP WestGrid October 2017. So now ls. If you do ls, you list all the files and the directories inside this directory. So you will have there is a README file and there is a script get node workshop.sh. There is a directory slash which I put there a copy of the slides we present today. And there was a directory sources where I put all the examples. So if you did some mistake by changing the present example, you have always the possibility to find the original version. And I put also some other programs for OpenMP. So that's for curious people. When you can use them later to learn more about OpenMP. The first thing you need to do is to use this. You need to use this script get node workshop.sh. So we have created the reservation for especially for this webinar. So this script will give you access to compute node. It's an interactive job. So access to compute node with 4 cores. And on Grex we don't have interactive jobs, so this script will work only for today because the reservation will be released just after the webinar. So what you have to do, just type /get. So I think it's not working. Why? Yeah. They can just copy again. So give me just a second. I will change the script. So I have changed the script. So you have 2 options. Either you edit the script and remove the option -x, or copy again the whole directory. So you can remove the first directory you copied and copy again from Global Scratch Workshop. Once you have done this, you have just to submit the script by typing /get. So it will give you something QSub waiting for job. So it means that you have submitted an interactive job. So the system will it will take some time, and your job and you will be assigned a node with 4 cores. So once you submitted this script, so you will end up on one of the nodes reserved this webinar. At the end, so you will have something like your username at node with a number with 3 digits. So, for example, node 131 or node 200, it depends. So you can keep that now. After some time, we will come back and add other options. When you have access to the interactive job, so you can just type this command: export OMP num threads =4. I will explain later what is the meaning behind this? Now, during this session, we will talk about OpenMP. So first, I will introduce what is called parallelism and concurrency, and I will talk about the types of parallel programming and parallel machines. Then I will give some definition about the construction of OpenMP. Then I will introduce some syntax and directive used in OpenMP. So for example, we'll use a program called Hello World, so a program that just prints a statement. We'll also talk about work sharing. For OpenMP is all about work sharing. It means share the work between the different cores. And for this, we use loops and sections. I will also introduce one of the most common problems in OpenMP. It's called fault sharing and race condition, and I will tell you how to avoid this. At the end, I will introduce some construct of OpenMP, like critical and reduction. And I will finish with some conclusions. So the objective from this session is not to become expert in OpenMP, but just to have some information to start with and where to find the information you need. So the objective is to introduce a simple ways to parallelize the programs. This means we start with a serial program, add some directives, some OpenMP directives, to have a parallel program. The OpenMP directives are three. There are directives which we add to the compiler. There is a runtime library and environment variable. We'll explain all this later. So during this session, we will learn how to use OpenMP. So we will learn how to compile and run an OpenMP program, how to create threads and split the work over the threads available. We'll know how to use loops and sections in OpenMP and introduce some construct. So introduction to parallel computing using OpenMP. So before going to parallel programming, we start by developing a serial program. So once you have a serial program that works, first thing to do is to test the performance and try to optimize the program. Because even if a serial program can be optimized. The compiler will give you some optimization, but it's possible to optimize by yourself. For example, if you have some additional operations that are not needed, because when you develop a code, sometimes you add some operation just for testing and you forget them later. So it's better to review again the program and get rid of all the unnecessary operations. Now you have is optimized and works, but when you the real world, you will have more problems because you need to run multiple programs. You need to study large and complex problems. All these operations are time consuming. So to gain in performance and run your program fast, so you need to use parallel machines. There are two types of parallel machines. We'll talk about this later. So you need to use parallel machines or multi-core machines. So the idea behind parallel programming is to reduce the execution time. So we use many cores or many CPU to reduce the time. For example, in this figure, we have a serial code that goes for a certain time. Now, if we can find a way to split this work over 4 cores, for example, we can theoretically reduce the time by a factor of 4. But sometimes we can have less than that. Depends how the program is written and what kind of the operations we use. So the main concept behind parallelism. So first, what is concurrency? Concurrency is a situation where many tasks are running at the same time, but not necessarily in parallel. So in addition to concurrency, if we can find a way to run this task in parallel, so we get to what we call parallelism, which is considered as a subset of concurrency. Now, what do we mean by parallel machines? So for parallel machines, there are two types. So for each type of parallel machines, there is a type of parallel programming. So the first type of parallel machines, it's what we call distributed memory machines. In this case, we have just, it's like what you have many computers you put in, together, and the connection between them is made by network. So you have communication via network. The second type of machines is called shared memory machines, which means that in one computer you have many cores, and all these cores share the memory. So the communication between the different cores is made via shared memory machines. So all the processors share the same memory. The variables in this case can be shared. So variable can be seen by all the cores, and some variables can be private. Each core has its own variable. In the case of distributed memory machines, all the variables are independent. So each computer or each CPU has its own variables. So for distributed memory machines, the type of parallel programming is mostly MPI-based programming. And for shared memory machines, the type of programming is called multi-threading or OpenMP-based programming. That's the subject of today. So what is the difference between the two parallel programming? So the first distributed memory machine for multiprocessing or MPI-based programming. So the communication is made via the network, and in the second, the communication is made via shared memory. The first one, MPI, is difficult to program, but its advantage is very scalable. For OpenMP, so it's portable and it's very easy to program, but not always very scalable. So now, what is OpenMP? OpenMP is an application program interface. So to use it, you don't have to install anything. When you install, you have your compiler, you have already access to OpenMP. So OpenMP is a library used to divide the work among the available threads. So we use it to transform a serial program to parallel programs. It's supported by many compilers. I just cited here Intel and GNU compilers. You can also use PGI or something else. We use it for C and Fortran. To know more about the compilers that support OpenMP, you can go to this, you can follow this link, and you will find more information about the compilers. So OpenMP comes in three different parts. The most important part, which is mostly 70 or 80% of the OpenMP, is compiler directive, which means that there are some directives which we add to the program, and these directives are interpreted when you compile the program. The second part is called the runtime library, which is just executed when you run the program. We will see examples about this. And the very small part, which is environmental variables. So there are some variables we can control from outside. When you compile and before you start executing your program, you can control some variables from outside. For instance, the most important variable is the first when I told you in previous slide this export OMP num thread equal 4, for example. This is most important because you tell your program to use this number of cores. So how to construct an OpenMP program? So there are 3 layers. The first layer is the application itself. So you have to write this serial program and to start with. So once you have this serial program, we go to the second layer to implement OpenMP. So add compiler directives, runtime library, and environmental variable if possible. Once you have this, so it comes to the third layer, the last layer. So you need an operating system and access to these compilers. So you have to compile and run the program. Now, what is the OpenMP programming model? How it works? So for OpenMP, we start for using a serial program. At some point of the program, if it's possible to run this portion of the program in parallel, you can create threads, which is here fork join. So at some point, we create threads and do this region in parallel. For example, in this figure, we have 5 threads. So at this point, we create 5 threads and do the computation. At the end of the parallel region, all threads will join, and only the master thread, thread equals 0, will continue. The second portion of the program, we can create, for example, it depends how many, we can create, for example, 4 threads and continue. So in some region, we can also fork, we have what we call nested regions. So we start with the master threads and create threads in response as needed. At the end, so the parallelism is added incremental, that is, sequential program evolves into parallel program. Now, during this session, we will learn how to use OpenMP by simple examples. So the first 2 examples, I will just use a simple program that prints a statement, hello world. Using this program, we'll learn how to go from serial code to parallel code. We'll know how to create threads. And I will introduce some constructs of OpenMP. I will also use the same program to introduce the loops, how to use loops and sections. Second part, there are 3 examples. So in example 02, I will introduce the problem of race condition, which is very common in OpenMP. If you know how to avoid this kind of problems, you can program many things in OpenMP. As a solution to avoid this, there is what we call the SPMD model, single program multiple data model, as a solution to avoid the race condition. And we will see that this model will not solve the problem because we can use it, for example, to get a good result, but we will not gain in speed. To gain in speed, we'll introduce some other construct to control more how the data is shared and so on. So before going further, I will just introduce some OpenMP syntax. As I told you before, the most constructs in OpenMP are compiler directives. So depending what you use, C or Fortran, there is certain syntax. To use OpenMP, you need first to include the header. For example, if you are using C or C++, you need to include this, include omp.h. If you are using Fortran, in Fortran, use modules. Use omp_lib. So this, when you use this, you enable OpenMP. You have access to a runtime library and everything. Now, OpenMP is if you have a program, you cannot, for example, put one command and the program became parallel. No, you have to define a region, then add the directive there. For example, if you are using C, so the parallel region in C, it's initiated by this command, # pragma omp. So # pragma omp parallel. If you are using Fortran, so it's $omp parallel. And like all instruction in Fortran, if you start one instruction, you have to close it. Here we have OMP parallel, so we will have OMP and parallel. So there is only the slight difference between C and Fortran. Otherwise, all the commands are the same. So the first thing to do is to define the region you want to parallelize and add this directive, # pragma omp parallel for C and $omp parallel in Fortran, and of course the header and the module. Now, where to put the parallel region? For example, in this slide, if you go to this second figure, we have a block of code. We have many entries and exit. So you run your program. At some point, you jump out of the program. After that, you go inside the same block. This is a non-structured block. So this kind of block, you cannot apply OpenMP. It's very difficult. So to have OpenMP, you need a very structured block. For example, you have one point of entry and one point of exit, like the first figure. So in this case, it's possible to implement OpenMP. So in this case, just add # pragma omp parallel. This is the code in C, and you have already your parallel program. Now, how to compile and run an OpenMP program. So let's suppose you have already written your program and you have access to GNU compiler. So to compile your program, you need to add some flags. And there are many flags, depends what you are doing. For example, but if you want to use OpenMP, you have to add this option -f OpenMP if you are using GNU compilers. If you are like GCC or GFortran, if you are using Intel compilers, the option will be -OpenMP, and it accepts also -f OpenMP. If you asserted also the others, PGA, for example, you have to add -MP and so on. So using GNU compiler or Intel, you will compile your program and you will get your executable. Now, how to run it? Before running the program, you need to set the environment variable with the OMP num thread. So you tell your program that I use this number of threads. For example, you cannot use 100 of threads because you don't have 100. For example, on Grex we have nodes with 12 cores. So if you want to use 12, so you need to put OMP num threads equal 12 in your PBS script or so. And, for this webinar, the maximum you have is 4. So you need to type first export OMP num threads equal 4. Now, if I go back to the terminal, so I suppose you all submitted an interactive jobs, and you got something like, for example, in my case, I got my username Kiraj at node 10. So I have access to node 10, and I have 4 cores. So what I do first, I have to set the number of threads. Export OMP underscore num threads equal 4. So everyone who have already access to a node has to type this command: export OMP num threads equal 4. Now we'll go back to the slides. So now if you have already your executable to execute, just type the name of the executable. So our first example, so now go to the directory example 00, and you will find, we'll start with the sequential program, because there are some people who just started programming, so we'll start with the first simple program, which runs in serial. So there was a program called Hello C sequential with a serial, and there was the same in Fortran. So the program is very simple. Just print a statement, say print hello world. So you can go to the directory. So if you are familiar with C, C++, just use GCC, hello C, sequential, and you will compile your program. In Fortran, use gfortran, the name of your program, and you will get an executable with a.out. As option, you can add -o, the output, you give the name of the executable. If I go back, I do the same now. I have to go back to the folder. So I go to example 0. So in each directory, I have provided some script to run the programs. I have already provided some files with the TXT, extension with TXT. These are examples from the output when you run the program. So when you run interactively, you can check if you get a similar output in this text. So I have also provided make file. So there are 2 make files, one for GNU compilers and one for Intel compilers. For example, if you, I set the default for GNU compilers. Now, for example, if you want to use Intel compilers, all you have to do is to copy makefile.intel to makefile. Or if you want to switch back to GNU, just copy makefile.gnu to makefile. To use the makefile, just type make, and it will compile all the examples, except the template. The template, just working file. We'll talk about that later. Now, if you want to remove all the executable created using make, just type make clean. This will remove all the executables. So make to compile, Now, if you check with ls, you will see some file with .x. These are the executable. So the first program to execute is hello C sequential. So just dot. So just a simple program that writes hello world. So there is nothing much to learn from this. So go back to the slides. So this is the program in C, just print hello world, and the same in Fortran prints hello world. Now the next example, so you have two templates, hello C OMP template.c, hello F90 OMP template.f90. So what do you have to do? So if you are familiar with C, use the C template. If you are familiar with Fortran, use the second. So all you have to do is find a way to add this header, include omp.h, or in Fortran use omp_lib, and add the directive to create parallel regions. Then try to compile and run the program using 4 threads. So I go back to the terminal. So I have this template hello C OMP template.c. So you have here added some comments. So add OMP directive here. So you have to replace this line by an OpenMP directive, which we have seen already, which is hash sign pragma OMP parallel or something. I don't know. You have to figure out what to do here. And there is another one here. So basically, you have two comments to add, and your program will become parallel. So I will give you 2 or 3 minutes to figure out. And of course, I added some comments, so you can just read the comment before the line where you need to put instruction, and you will figure out what instruction you have to add. For example, this add the header. So you know what is the header, so add it there. And here add OpenMP directive to create parallel region. So if you did so, you can try to compile. So to compile, for example, using GCC, just type GCC minus F OpenMP and the name of the program. For example, we'll just compile it without changing anything. So GCC minus F OpenMP hello C OMP template. So if you compile directly without changing anything, you have some warning. Data definition has or storage class. So there is a problem. So we cannot get an executable with this. I assume that everyone has enough time to look at the program and change it. But if you didn't succeed, you can just check the solution. So you have you have to check for example, hello COMP.c. So I have this example on the slides. So what to do? So if, you have the first serial program, which is, for example, print hello world. So all you have to add is this include std input output at the beginning, OMP.h to enable OpenMP. If you are using Fortran, you have to use this module, use OMP-lib. And to transform this portion of the code to parallel, just add hash sign pragma OMP parallel, and in Fortran just exclamation mark dollar OMP parallel and OMP and parallel, and your program will become parallel. Now you can run the previous program. So in your directory, just type make. It will compile all the programs. Now you can execute. We have already exported the number of threads to 4. So if I execute now this program, hello COMP.x. So it will print hello world 4 times. Now instead of, for example, of using 4 cores, I can just use, for example, 3. So I have to export again the number of threads to 4. So export 3. Export OMP non-threads equal 3. So now if I execute the same program, I will get 3 times hello world. I'll go back to 4. So you will get the same using Fortran also. Now the next example, we use the same example, but we have to add more construct. So for the next example, so we have to use the type of variables. For type of variables, the best practice is to use always default none. This means that you need to define all the variables. If you are already using Fortran, for example, there is this instruction at the beginning of Fortran code, which is called implicit none. If you use this, you tell the compiler that all the variables have to be defined. But if you don't use this, the compiler can take, for example, all the variables that start with I as an integer. So if you forget to define all the variables, you can have some conflict between variables. So the best practice is always to use this in Fortran implicit none. And for OpenMP, for variables, it's better to start with this default none. So you tell the compiler that I need to define all the variables. Now I talked already about private and shared. Because on shared memory machines, we have the same memory. So we can assign a value which is shared all over the cores. So each core will have access to this variable shared memory, and it can also have its own variables or its private variables. So for this example, there is a template called hello world in the same directory, hello world C template .c, or the corresponding one using Fortran. So we can add other instruction, for example, to get a thread rank. So for example, if you are using 4 threads, So the threads are labeled from 0 to 3. If you have 12, are labeled from 0 to 11. So there was this function OMP get thread number. So this function returns an integer, which is the thread rank. There was another function that returns an integer also, OMP get num threads. For example, if I want to know how many threads I have, so it's OMP get num threads. There was another which is not very often used, but you can use it. For example, when you develop your program and you try to test, instead of using export OMP num threads equal 4, for example, at the beginning before you start your program, you can just set this variable inside the program and set it to 4 once, then execute your program. But for production, you need to remove it because before you compile your program, you don't know how many cores you are going to use. For example, if you are working on a system that has 32 cores and you set this for 32 cores and you copy your program to a system which has less, so it's not possible to use it. So it's preferable to use it just when you develop. For production runs, you have to remove it. And you set it as an environment variable. There is another function that returns real, OMP get W time, which means if you execute this function at a certain point, it will give you the time at that point. Now, if I execute it at the other point, we'll get the time when I get there. And if I compute the difference, so I can have the time used in this portion of the code. This is the better way to start with, because when you run a serial program, you don't know exactly which region of the program takes more time. So if you add this function between 2 points, you will have the time spent there. So like this, you can define the region that takes more time and work on it to run it in parallel. So now go back to the terminal. So the template is hello world COMP. So here again, so there are some commands. So just follow the command and try to figure out which directive you need to add. Here, for example, I defined the number of threads equal 4, so just set it once. So here I printf start the program, just to print that the program starts here. Here it says set number of threads to num threads. So here we just we can add the function OMP set num threads, so on. Now to know how many threads are available. This is very important. Now I didn't start the parallel region yet, but I want to know how many threads I have. This is just a statement to print that variable. Now I start the parallel region. So here you add the command to create parallel region. This is ID equals, so I want to know what is the ID or the rank of each thread. Here I want to know how many threads I have, and now I am in the parallel region. Then in this line, so the program will print hello world, my ID is equal to, it will print hello world, it will print the ID of the thread and the total number of threads. Now at this point the parallel region, this is the end of the parallel region. Now here I compute time at the end of this parallel region. Then I make a difference between the two times. This will give me time spent in the parallel region. At the end, I will print all the information. Once you figure out to add all this information, all this directive, you can just compile using GCC minus F OpenMP, the name of the program. If there was no error, should be able to get an executable and I'll go back to the slides. So basically what I did here, so OMP set num threads. So I defined num threads equal 4 as a parameter at the beginning. So I set the number of threads to 4, so I don't have to export this type if I don't want. But this is usually we use environment variable from outside. So then start time equal OMP get time. So I want to know what is the time at this point. Then the parallel region starts from here, pragma OMP parallel. So only these 4 lines are is the parallel region. So OMP parallel default none. So I assume that all the variables have to be declared. So I have a private variable which is ID. Each thread has its own ID which is private, and there is a shared variable n thread, number of threads, the total number of threads. So all the threads know how many threads we have. Now, when in the template I showed you earlier, I added OMP get num threads outside the parallel region. So what will be the answer? Now, if you add this command outside the parallel region, you will get 1, because outside the parallel region there is no thread. The threads are only created when you start parallel region, which means inside after this pragma OMP parallel. Inside, so here I used 4 threads, so the program will will print that we have 4 threads. So we can execute the corresponding program. So this you can just go. I have already typed make, so I have compiled all the program at the same time. So hello world. I can execute the first run program, for example, omp.x. So it prints start the program. I am out of the parallel region, and the number of threads is equal 1, because out of the parallel region the threads are not created yet, so only the master thread is present, so we get 1. Now if we start the parallel region, so the program will print hello world, my ID is, the first thread will have an ID equal 0, and it prints the shared variable, which is total number of threads equal 4. And at the end it gives the time spent in the parallel region. Outside also of the parallel region, if I try to print again the number of threads, I will get 1. So this is very important, because we cannot talk about threads before creating them. So threads are exist only in the parallel region. You can execute the same program by changing the number of threads. For example, you can go back to 3, for example, export OMP num threads equal 3. So it will not work with 3 because I set already the number of threads inside the program. So if I remove that option and use export OMP num threads from outside, so I will be able to use the thread because in this program it's fixed to 4 already. So this is just the output from when you execute this program for using 4 threads. So my ID is equal 0, total number of threads is equal 4, and so on. Now to go further, so in each program we use loops. For example, in each scientific application, you need to run, for example, to compute the set, to use the numerical integration, or so. There are many computations that use loops. So loops, it depends if you are using Fortran or C. In C, we use for e equal 1 to n do something. In Fortran, do something and do. So for OpenMP, it was the same. So you need to create a parallel region. For example, use pragma OMP parallel. Then if you have a for loop, so just pragma OMP4. In this particular example, there was no command between pragma OMP parallel and pragma OMP4, so we can just combine both instructions into one. So we'll have pragma OMP parallel 4. The same in Fortran, so OMP parallel, then create loop OMP do. So we can combine both to OMP parallel do and OMP and parallel do. So here how it works with loops. So you have here pragma OMP parallel, pragma OMP 4, and add the loop you want to run in parallel. So what happens? So your program starts from serial, and at this point it finds pragma OMP parallel 4. So it creates the threads, for example 4. When the computation are finished, everything will be joined, and the program continues as serial. So in addition to loops, we can also use sections. Sections are useful when you have, for example, in one portion of the code, you have different calculations which are independent. For example, if you are computing something as a function of x, y, and z direction, for example, you can assign one section for x calculation, and especially if they are independent, you can create 3 sections. You can create more sections. It depends on how many independent portion of the program. So you start pragma OMP sections, and each section starts OMP section. In Fortran, it's the same: OMP section, OMP end section. Now you can go to the folder 01. So to change the directory, here is the same. We have always slides. We have C and Fortran programs, which are the same. So for each C program, there is a Fortran program. There are scripts to run, and there is a make file and the readme file. So for this one, now you need to open a template. Hello World. Loop, then C or Fortran, OMP, template. So here again the same. So there are some missing directives. So there are some comments here. Add OMP directive. So you need to change this and add all the directives, number of threads, what to add here. Add OMP directive here. Then try to compile. So, for example, here we have add OMP directive here. Here we need to create a parallel region. So you need to add directive that creates parallel region. Yeah, it can take 3 or 4 minutes to figure out what to put. Here there is a comment, for example, I said here if ID equals 0 and threads equal. I want to know how many threads I have, so I don't need to execute this command by all threads. So we just pick the first one, so the first thread, and it gives me the number of threads. For this, we can, instead of this line, if ID equals 0 and threads equal OMP get num-threads, there is a construct in OpenMP which is called OMP single, which means that the first thread that arrives will execute, and the others they just go. Now, if I go back to the slide, so in this template, all you have to do is to add this include omp.h to enable OpenMP. Here I define the number of loops called 8, so it can be something else, depends what is the problem. So I create the parallel region here, pragma OMP parallel. And for variables, I use default none, private ID, shares the same as we have seen previously. So ID equal OMP get thread number, so each thread will get its ID. Now, if the ID is equal 0, I will compute the number of threads available. This line can be just replaced by this command, pragma OMP single. It means that the first thread that arrives here will execute this command, and the others just go through it. Now, then I create the loop, pragma OMP4, and for this loop, so I have a loop from 0 to number of loops. It should be in C number of loops minus 1 because we started from 0. So this will print hello world. It will give my ID, and it will give the value assigned for this thread. Now, if I go back and execute the program, so now we need to compile all the programs. Just type make. It will it will compile all the programs at the same time. Now, if I want to execute the the template, the program that corresponds to the template we are working on. Just name hello world C. It can take Fortran and loop Fortran OpenMP. So you see, for example, if I have 8 the loops. So the index for the loops starts from 0 to 7. Now, for example, here it says hello world, my ID is equal to 0 of 3, because maximum of threads is equal 3, because previously I exported the number of threads to 3, I didn't change it. Now if I want to change it, I can just go export to 4. Export OMP num threads equal 4. Now if I execute again the program, so it gives you hello world, my ID is equal to 2 or 4. So it says that my ID is equal to, and the total number of threads is 4, and I get the value 4, and so on. If you execute the same program many times, you'll see that the values are, the order of the values is different. This is very important because it depends which threads comes first. So the first time maybe the thread 0, the second time maybe the thread number 2, or so on. So this means that even if the order is different, this may not affect the result. So you have to check the result before starting production using your program. So this is just the same program using Fortran, so there was nothing changed. This is the output. If you now, instead of, for example, if you use 2 threads and you have 8 loops, so you see the output. So you can play with the program, change, for example, the number of loops, and change the number of threads, and see. For example, if you have 8 loops and you use just 2 threads, so the first thread will take the values 0, 1, 2, 3, and the second will take 4, 5, 6, 7. If you have, for example, 8 loops and only 3 threads, so the first thread will take the values 0, 1, 2, the second will take 3, 4, 5, and the last one will take the remaining just 2. We don't have now so far just for this small program we basically have most used construct in OpenMP. So we know how to create threads in C and Fortran. We use in C we use Pragma OMP parallel, and we create a parallel region. In Fortran we start OMP parallel and we close it with OMP and parallel. And of course you need to include the header or the module, depends on C or Fortran. If you want to know the number of threads, you can add this function OMP get num threads. If you want to use, for example, in some calculation, you need to have the calculation as a function of the thread rank. Use this function OMP get thread number. For example, instead of setting the number of threads from outside just for testing, you can set it inside the program using OMP set num threads, but remember to remove it and have the possibility to change the number of threads using environment variable OMP export OMP num threads equal 4, for example. I have also introduced the function called OMP get WTime. For when you develop your program, it's good to use it to see how long it takes to run, for example, a portion of code. But for production, you can remove it later because it's not necessary when your program is optimized and finished. I introduced also another construct, OMP single. For example, in some parallel region, you need to execute one command just once. So, for example, the first thread that arrives there will execute it, and the others will not see it. So it's possible to use, for example, the condition if id equals 0, execute this command, or replace this command by OMP single. For variables, we have seen that it's possible to use shared variables and private variables. Private means each thread has its own variable. Shared, the same variable can be seen by all threads. And remember to use always the default none. We have also seen how to use work sharing, loops and section. We didn't run the example for section, but it's the same principle as we have seen for the loops. You can have a look to the programs and run them. You can easily understand them. So to introduce loops and sections, so you need Pragma OMP4 in C and Pragma and OMP do, OMP and do in Fortran. Now, if you have Pragma OMP parallel, then followed directly by Pragma OMP4. There is no instruction between them. You can combine both to one single line, Pragma OMP parallel 4. And it's the same for Fortran. Now, so far we have just used the simple example to learn how to use OpenMP. Now we move forward and use some example that is used in many applications. Whenever you develop a code or try to solve a program, you will end up by something like an equation to integrate or something. So for this we use for numerical integration if you don't have analytical equation. For this example, we didn't take just any function. We have chosen a function where the solution is no. If you integrate this equation, this formula from 0 to 1, you will have the number pi, 3.14. So now what to do? For example, you have another function, you can just do the same. So this function can be replaced by sum of this parameter. So what you do, you just divide this area into different small bins, then compute the area of each bin. At the end, add them together and you will get the final result. So this is the serial version of the code to compute pi. So you need to initialize, I have here a variable called sum, total sum. So I have to initialize the variable to 0 at the beginning. Then I do a loop to scan all the bins on the different small areas. Then for each I compute the value of x with this formula. Then I add the sum. At the end, I compute pi. So you can just run the serial code, for example. Previously, I was talking about optimization. For example, here the factor 4 and step. I can add them inside the loop, but it's just waste of time. For example, imagine if you have to compute, there are only just two more operations. For example, if you do the same, if you put them inside the loop and you have to run this loop for 2 million steps, for example, so you have added 2 million times 2, so 4 million operations. But since it's a common factor, you can just use it once at the end. So it's a sort of optimization of the program. Now if you go to the, I need you to go to the next folder, example 02. So the first thing to do is to compile all the programs, make. Now if you want to run this program to have the value of pi, so compute C sequential. So here, for example, from the names of the programs, if the program contains a character OMP, it means it's an OpenMP program. If it contains sequential, so it's serial. So if it contains F90, so it means Fortran, or otherwise it's C or C++. So so the value of P is 314. So that was computed using, I think, 20 million steps. And it takes 0.34 seconds to have this value. Of course, we don't need 20 million steps. You can have this value for example, 20,000 or something. I just put this number to have. Now go back to the slides. So this is just to show how to compute pi. So we have transformed the integral to a sum of then compute add the sums at the end, put everything together, we get the number pi. Now the next example to do is to take one of these templates, either in Fortran or C. So do the same as previously. So you need to add Pragma OMP parallel to create a parallel region. Include the headers also to use OpenMP. And use the variables shared and private. And don't forget to put default none. Then optionally, you can also add OpenMP get W time to see what time spent in the parallel region and try to compile the program. If I go to the template, so this time I will just open Fortran template just to change. So here, so in this program, so I defined as a parameter at the beginning, so the number of steps, 20 million or so, yes. Then I need the width of each beam, so I have to divide it's 1 over number of steps. Then I define all the variables I need, pi to give the number of sum, and x. I define all other variables for start time, end time, and elapsed time. So here I just used another function to compute time, called CPU time in Fortran. There was also, we can use the same function from OpenMP. So there is no difference. So what you need here, so the parallel region starts from here. So I'll add OMP directive here to create parallel region. Then do the calculation and so on. So here important because if you add something here, you have to close it. So there are two places. Then you compute the time at this point. Then compute the difference between two times and print the result at the end. You will get the same if you use C program. So this will give you something like this. So to create a parallel region, just pragma OpenMP parallel, default none for the variables, private I. So this index will be private for each thread. Then the shared variables x and sum. So these two variables are used by all the threads at the same time. Then compute. Now, if you try to execute this program, so either if you're finished with the template and changed everything, you should be able to compile it and get the executable and use it. Otherwise, just use this. The corresponding version will be compute by OpenMP race. So make by C OpenMP.x. So you see. So if I execute this, so I didn't get the right value. This is the first problem, and it takes more time. Previously, I used one thread and I got good result 3.14, and in less than 1 second. But now I used 164 seconds and I got the wrong result. If I do the same again, I will get another value which is wrong also and another time, and so on. So it means that something is wrong. So we didn't share correctly, we didn't control correctly how the variables are shared. This is what we call race condition in OpenMP. If you can avoid such problems, you are already ready to program using OpenMP. So this is the output. So if you execute once, you get one value, another time you get another value, and so on, and the program takes longer. So we have two problems. We have a wrong answer, and the program is slower than the serial program. So now we have to solve this problem. So how to solve this problem? So to solve this problem, there is a technique called SPMD model, single program multiple data. So it means that you have one portion of the code that it's a single program that be executed by multiple that handle multiple data. So for this model, what to do? So we can just take the sum we have previously in our example and promote it as an array. So we assign a local sum for each thread. It will compute the local sum as a function of its ID. So the program will be something like this. So for I equals 0 plus ID, computational as a function of I and ID. So it's like a cyclic distribution. So for the thread 0, we will give the iteration 0, 3, 9 for thread number 1. Here if we have 3 threads, so the first one will take 0, 3, 6, and so on. The second will take the iteration 1, 4, 7, and so on. Thread number 2 will take 2, 5, and so on. So now you can go to the folder example 03, and there is a program compute by F90 or SPMD, which implements this model. So go back to, so I have to go example 03. So I have to compile all the programs using make, because we have already make file and everything was set. So now if I execute the program, we can see the program first, compute C SPMD dot SPMD simple dot C. So just so we have created the local sum ID equals 0. So before computing any sum, you have to initialize the value to 0 at the beginning. Then each thread will add this value. At the end, we will put all this local sum together and print the last result. Now, if I execute the program, compute C. So I set already inside the program to change the number of threads from 1 to 4. So if I execute using one thread, so I get 3.14. The time is 0.34 seconds. If I use 4 threads, so I get 3.14, and the time is 0.49. So the good news that we got a good result, which is 3.14, no matter how many threads we use. But there is the second problem of the time. Instead of speeding the program spends more time. So we need to solve also this problem, because if we use 4 threads, theoretically we can reach at least 4 times speed, maximum of 4 times speed, or a little bit lower than that. So what to do to gain this speed? So compile and run. So this time we have, so this is just the output. So we have a good result, 3.14 for whenever you use, depending on how many, it doesn't depend on how many threads you use, but the program is slower. So what to do to speed up the execution of this program? So to do that, we need to control how the variables are shared and also avoid the race condition. So basically, we need to do some synchronization and control how the threads work. So for synchronization, there are many of them. So for example, there is barrier. So which means that at some point of the program, we put a barrier. So we ask the program that all threads must arrive at this point before going further. There is another type of synchronization, which is material exclusion. So we put at some point of the program, so one thread at a time can execute this command. For example, if you have one command after this, so you tell the program that only one thread at a time can execute. So doing this will avoid this problem of race condition. So to do synchronization, there are many constructs. For example, you can use the critical, atomic, barrier. So I will not have time to introduce all of this construct. So what is the synchronization? Synchronization is to control how the threads work. But if you synchronize a lot, so you can reduce the performance of your code. If you synchronize more, your code will become like serial, so you didn't gain any performance. But if, you need just to use it if it's needed. So I will try to define some of this construct. So barrier. For example, you have this parallel region. So then put pragma OMP barrier. So I will tell that each thread wait. For example, the first thread finish this portion of the code and arrives here, and it will wait until the others finish to continue further. So for critical, so this is the same concept, pragma OMP critical. So it says that only one thread at a time. So if the first thread arrives, it will execute. And if another thread arrives at the same time, it will wait until the first one finishes. There is a construct which is atomic. That's the statement, local statement. It can be introduced using pragma OMP atomic. The most important construct in OpenMP is this one, reduction. So, for example, we have seen when we compute the sum, we need this sum is shared by all. So we got this race condition because each thread tries to read or write this variable, so it's messed up, and at the end we get wrong result. So in OpenMP we use this reduction. How it works? So in a parallel region or work sharing construct, if you add this construct reduction operation and list of variables, the operation can be, for example, the sum, minus, or multiplication, depends. So this list of variables, so whenever you add this construct, so a local copy of each variable from the list will be created. So each thread will have its own copy. Then it will be initialized according to the operation. If you use plus, the local variables will be initialized to 0. If you are working on multiplication, it will be initialized to 1. Then each thread will update its own copy. At the end of the parallel region, all the local copies will be combined together. You don't have to do anything. The program will do this. When you just use reduction, the program will do all this. You don't have to initialize the local copies. It will be initialized by the program. And at the end, it will be added and combined to the last result. So here how it works. So pragma OMP parallel for the loop. Reduction. plus average. For example, here I compute the value average. Average is a global value, so I have to initialize it first. But inside the parallel region, I don't have to initialize because when I use the reduction, it's initialized automatically. So now we can go to the folder, the last folder, example 04, and there are some templates you can use. Change them and try to. So all you have to do is add the directive to create a parallel region and the loops, include the headers and the model. So for one template, you can use SPMD pattern we used previously. In another version, add reduction. And try to compile and run the program. So I go to the folder example 4. Again, if you want to compile all the programs at once except the template, just type make. Everything was already set to. Now, if I take one template to change, reduction, for example, VI compute by C1P reduction. So this is the template for the reduction. So we have almost the same program, so number of steps, compute the step, the width of each beam. And here I defined maximum of threads to 4 because in this webinar I have access only to 4 cores. The main program starts from here, main. So I defined the variables for time, start time, end time, elapsed time. So this is variables for pi and so on. Total sum. So I have a global variable total sum. Then I have here you have to add an OpenMP directive, and there is a comment to figure out which one to add. Set number of threads. Here I want to know what time is it at this point. So add OMP directive to know which time is it. I've seen it's OMP get W time. Here start a parallel regions, you know already how. So pragma OMP parallel and so on. Here I want to know how many threads I have. I am inside the parallel region, so I can talk about threads. So here this statement, I want just to print it once. I don't want to print it, for example, 4 times. So there are 2 options for this. I can use if ID equals 0, print this, or I can use pragma OMP single. It means that only one thread will execute this statement. It's the first one that arrives there. Here I compute this is the main loop. Compute that. Then the final result here and the end time. If I try to execute now, so reduction. So in the program it's set already to change the number of threads. just to avoid running 4 times the same program. We change inside. So the output is if you run the code, you have always the code result 3.14. Now, if you use one thread, the program takes 0.40 seconds, with 2, 0.20, with 4, 0.10. So we have almost 4 times speed. We have a good result and speed. So we still have 15-20 minutes left. So what we have seen during this presentation, we have seen how to use OpenMP. So OpenMP consists on creating threads. To create threads, you need, if you are working on using C or C++, you need to add pragma OMP parallel, and what comes after is parallel region. The same in Fortran OMP parallel, and close it with OMP and parallel. And remember that outside of this block, only the master thread works, so we have only one thread. You can just talk about threads inside this parallel region, and to share the work for when we use loops or sections. For the variables, remember to add default none, because it's very useful for debugging, because if you forget to declare any variable when you compile, you will see there is a warning about this, so you have to define your variables. And you have 2 types of variables, where private variables. So private means that each thread has its own variable. Shared, which means that this variable is shared by all the threads. So each one can see this variable and can read it or change it. To use OpenMP, you need to use some environment variables and runtime library. For the environment variables, the most important is this OMP num threads, which you use before you run the program, because when you compile your program, you don't know exactly how many threads you are going to use. So compile the program and set a number of threads before executing the programs. There are some other functions. You can use them when you develop, for example, your code, but they are not needed after that. To have an idea about time, you can use this OMP get W time. It's the same, for example, if you work in Fortran, there are functions to get the time. We have seen some constructs. For example, single construct, so it means that the statement that comes after is only executed by one thread. The most important to understand is this reduction. It's it's the most used, especially when you compute, for example, sum or something. To have more information about the runtime library and other constructs, you can visit this links. You will find more information about this contract and construct and others. Now, I want just to give this. For example, if you want, you have already your code, you compile it, you use OpenMP, and you want to submit it as a job, for example, on Grex or any other system. If you are using PBS script, so the most important information to add in the script is this: PBS minus L nodes equal 1, which means that you restrict your job to run only within one node. and specify the number of cores. For example, here I specified equal 4. You cannot, for example, use procs because your program cannot run across the nodes. It's not an MPI program. Then before you run, you have always to use this command export OMP num threads equal to number of threads you fixed here. So as conclusion, so OpenMP is easy to implement and easy to use. We use it for simple parallel programming for shared memory machines. It can speed the execution of your code, but it's not very scalable. For this, for example, if you have already your code and is running, you can run performance test. For example, if you are running on Grex, you have access to each node has 12 cores, so you can run the same code. For example, once serial using one core, then 2, 3, and 4, for example. Then from the time spent using all this combination, you can decide which number of cores is suitable for your program. So to implement OpenMP, first thing to do, you have to define the concurrent region that can run in parallel. You need to add the compiler directives and the runtime library. You need also to control how the variables are shared, so in order to avoid the race condition. And most important thing, you need first to test the program and compare to the serial version. Because if you did something wrong in synchronization, or there was this problem of race condition, you will get different results. So it's more important to test and compare to the serial version. For more information, there are some links where you can find more about OpenMP. And of course, there is always this WestGrid website event. You can go there and you can check all the current event and previous ones if you want, if you missed any.